Welcome to the Deep Dive, where we cut through the noise to get you well-informed, fast. Imagine an AI agent, not just assisting you, right, but skillfully operating your entire computer desktop. Navigating apps, solving complex tasks, totally autonomously. It sounds like pure sci-fi, but, well, it's getting real fast.
It really is.
Okay, so let's unpack this. Today, we're diving deep into a framework called Computer RL. And this isn't about, simple macros or basic automation.
No, not at all.
It's about intelligent agents that can actually understand and execute really complex tasks across your whole digital workspace.
Yeah, the scope is much bigger.
Our mission here is to explore how Computer RL tackles these honestly huge, long-standing challenges in desktop automation. We want to look at its core innovations and what its, frankly, impressive performance means for the future of how you interact with your computers. We've sifted through the research, the sources you sent, to pull out the key insights.
And what's really fascinating, I think, is how this research fundamentally re-examines our understanding of machine intelligence. It's moving AI out of those specialized kind of contained environments and into the messy, complex, very human-centric world of the desktop. That's a significant shift, a big step up in what we expect machines to handle autonomously.
Okay, so if it's such a potential game changer, let's be real. Getting AI to work smoothly on a desktop, it's always been a massive headache.
Right.
What's the biggest, fundamental reason previous tries just fell short? It's not just clicking buttons, is it?
No, not just clicking buttons. The biggest hurdle is what researchers call the inherent mismatch.
Mismatch.
Yeah, think about it. Our GUIs, graphical user interfaces, they're built entirely for us. For human eyes, human hands, human intuition.
Okay.
Machines, though. They prefer structured data, explicit commands. It's almost like trying to get a machine to read your mind when all it sees is, well, a picture of your thoughts. It doesn't have the underlying context we do.
Wow. Right.
And the prior approaches really highlight this difficulty. You take behavior cloning, or BC. It can be precise, sure, but training it for complex stuff is just prohibitively labor-intensive. It needs tons of manual annotation, basically showing the AI exactly what to do step by step.
Wow, okay.
And even then, it struggles to generalize. It sees something new or an error pops up. It often just breaks. It's brittle.
Right. Doesn't handle surprises well.
Not at all. Then you've got traditional reinforcement learning, or RL. Conceptually, great learn by trial and error.
Sounds promising.
Yeah, practically. Applying it to the desktop, it's been incredibly hard. The computational complexity is huge. It converges painfully slowly, and training is just inefficient. The sheer number of things you can do on a desktop, the states it can be in, it's vast. Traditional RL just couldn't scale effectively.
It really sounds like a foundational design problem then. Like trying to force a machine to act human in a world built for humans and then multiplying that by all the complex software we use. No wonder they hit a wall.
Exactly. That's the core challenge.
So, okay, we've laid out the challenges, the deep-seated problems.
Yeah.
But this is where Computer RL comes in, and it tackles these with what we call the triple threat of innovations. Let's peel back the layers on the first one. How these agents actually talk to the computer, bridging that gap.
Right. This brings us to the API-GUI paradigm. And the core idea here is, well, revolutionary in its pragmatism. Don't force the AI to just blindly imitate humans.
Okay.
Instead, let it smartly switch. It can use direct, efficient machine language commands, that's the API part when it makes sense, or it can use human-like visual interaction clicking and typing via the GUI when that's better or necessary. It gets the best of both worlds.
So it's flexible.
Extremely flexible. The way it works is pretty clever. They've integrated this large-scale, automatically constructed API ecosystem directly with conventional GUI operations.
Automatically constructed.
Yeah, and that's key. So the agent can use a direct command for, say, saving a file if an API exists for that in the application. But if not, or if it needs to, say, drag a slider visually, it falls back to mimicking human clicks and drags via the GUI.
Okay, but how did they build that API part automatically? That sounds like a huge task itself.
It would be, manually. But they use large language models, LLMs, to automate key steps. The LLMs help analyze task requirements. They actually implement the API using Python libraries and even generate basic tests for it.
Wow.
This massively lowers the barrier to creating new application-specific APIs. It makes the whole approach much more scalable and adaptable.
So it gives the agent options. A direct command if available, human-like interaction if needed. That sounds incredibly practical. Can you give us a concrete example, maybe a common task where this hybrid approach really shines?
Absolutely. Think about processing an image in GIMP and then inserting it into a LibreOffice Writer document.
Okay.
Or maybe monitoring system resource usage in the terminal, or doing complex table calculations in LibreOffice Calc.
Right.
The agent might use a direct API call for, say, a specific calculation in Calc because that's fast and precise, but then it might use GUI interaction to format the table visually or copy-paste the result into Writer because maybe there isn't a clean API for that exact sequence, or the visual layout is crucial. This hybrid model just gives it so much more versatility and efficiency.
Okay, that makes sense. Smart interaction is one piece, but even the smartest agent needs a place to learn, a massive playground, right? What were the problems with older training environments? And how did Computer-L manage to scale up so dramatically?
Yeah, the training environment is crucial. And past ones, like the standard OSWorld implementations, they were notoriously difficult, really resource intensive, often unstable.
Oh, yeah.
Yeah, they suffered from performance issues, freezing up, especially when you tried to run many at once. Network bottlenecks were a constant headache, causing connection failures. And critically, they just lacked native support for distributed training across multiple machines, multi-node clustering. That completely hamstrung any attempt at large-scale RL training.
So a bottleneck, basically.
A huge bottleneck. Computer solutions here are really comprehensive. They aimed for a robust, massively parallel system. First, they used a standardized, decoupled interface, the Agent Bench API, that makes integration flexible.
Okay.
Then, for efficiency, they implemented lightweight VM deployment using QEMU and Docker, basically running virtual Ubuntu desktops inside Docker containers.
Right.
It makes them super fast to spin up and incredibly resource efficient, uses way less CPU per instance.
Right.
And to get that massive scale, they built in distributed multi-node clustering. They link multiple CPU nodes using gRPC, that's a high-performance communication framework, and it's all managed centrally. Plus, they added web-based visualization and monitoring for real-time visibility. You can actually see what the agents are doing.
Wow. Several thousands of concurrent environments on a cluster. That is unprecedented scale. That's the kind of volume you need for these agents to actually learn complex behaviors. A huge leap.
A necessary leap, really.
Okay, so you've got the smart interaction, the massive training ground.
Yeah.
But even then, AI can hit plateaus, right?
Yeah.
They can get stuck. You mentioned this problem of entropy collapse where the agent just stops exploring new ways of doing things.
Exactly.
So how does Computer-L fight that? This is where Entropulse comes in. Tell us about this smart coaching strategy. How does it keep the agents learning and exploring?
Right. Entropulse is specifically designed to counteract that entropy collapse. It's a novel training method that ensures the learning keeps going by alternating between, standard reinforcement learning, the RL phase, and periodic supervised fine-tuning, or SFT, phases.
Okay, alternating RL and SFT. How does that cycle work?
So during the initial RL training, the agent tries to solve tasks. When it succeeds, those successful sequences of actions, the trajectories, are collected.
Right.
This collected data is valuable because it's high quality, it worked. And it's diverse, capturing different successful strategies from different attempts or slightly different agent versions.
Got it.
This curated data set is then used for the SFT phase. The SFT explicitly trains the agent's policy to have increased entropy.
Increased entropy, meaning
it enhances its ability, its tendency to explore, to try different things. It gets a renewed sense of curiosity, if you like.
Yeah.
And once the agent has this boost, this renewed exploratory capacity, a second round of RL training starts. And the second round leverages that brain boost to achieve even better performance. It's a clever loop to prevent stagnation and keep pushing performance higher.
So it's like giving the agent a targeted reset or, a brain boost just when it might start getting stuck in a rut. Keeps things fresh. Is that a fair way to put it? And what was the hardest part of making that boost work?
That's a great way to think about it, a targeted brain boost. The biggest challenge, I'd say, was making sure the data collected for that SFT phase was both high quality, you don't want to teach it bad habits, and diverse enough to genuinely increase exploration without hurting the performance it already had. It had to be a smart boost, not just random noise.
Makes sense. Okay, so beyond these three core innovations, the API-GUI, the scalable training, Entropulse, the actual training process itself sounds pretty sophisticated. Not just one step, but a multi-stage journey. Can you walk us through that?
Yeah, it's definitely a journey. It starts with behavior cloning, BC, cold start.
Cold start.
Meaning you start from scratch using BC. This initial stage is all about teaching the model the fundamentals, the basic competencies for interacting with the desktop. It does this by imitating existing user interactions, basically showing it lots and lots of examples of how things are done.
Okay, learning by watching.
Exactly. And the data collection for this is quite advanced. They don't just use one source. They use multiple advanced LLMs, even powerful closed source ones like Claude and Gemini, to generate diverse examples or trajectories for a wide range of tasks.
Using multiple models.
Why? To get diversity. Different models might solve a task differently or succeed where another fails. They then do what's called stratified analysis, sorting tasks into fully solved, partially solved, and unsolved. For the partially solved ones, they use the initial attempts to guide further data generation, refining the approach. For the unsolved tasks, they use a model pool, combining the strengths of several high-performing models to generate successful trajectories that maybe no single model could figure out alone.
Pooling expertise.
Precisely. And crucially, only the successful trajectories get aggregated and filtered for the supervised fine-tuning in this BC stage. This equips the model with robust desktop skills and a solid reasoning foundation right from the start.
That sounds like a really smart way to bootstrap the process. Get a high-quality, diverse foundation without relying too much on any single source or needing endless manual examples.
Exactly. It sets a strong baseline. After that BC cold start, the process moves to stage 2, reinforcement learning from verifiable rewards.
Okay, RL time.
Right. Here they use an extended algorithm called GRPO for optimizing the agent's policy step by step. It's a sophisticated RL method designed for more stable learning. But the really key part here is the reward framework. It's rule-based and verifiable.
What does that mean? Verifiable rewards.
It means the rewards are directly tied to observable, verifiable outcomes at each step. If a task is successfully completed, actions that were correctly formatted and actually contributed to that success get a reward of 1.
Okay.
If the task fails, or if an action was, say, formatted incorrectly or didn't help, it gets a reward of 0.
Simple binary reward.
Simple but powerful. It provides very explicit, interpretable feedback. It tightly couples the agent's actions with task success, step by step, rather than just giving a final score at the end. Each little interaction, each prompt response pair is treated as its own training instance. Makes the feedback loop very direct, very efficient.
Yeah, that explicit step-by-step reward sounds much more useful than just getting a vague good job or try again after a long sequence. It really helps the AI figure out precisely what worked and what didn't along the way.
It absolutely does. And then stage 3 is Entropulse in action, integrating seamlessly after that first RL phase.
Right, the brain boost again.
Exactly. As we discussed, it takes all those successful trajectories gathered during RL, the ones that led to that reward of 1.
And use them for that targeted supervised fine-tuning. This gives the agent that fresh burst of exploratory capacity, resets its learning curve in a sense, and allows it to dive into a second, often even more effective RL phase to really push for peak performance.
Got it. So BC to build the foundation, RL with clear rewards to learn effectively, and Entropulse to overcome plateaus and sustain that learning, a very structured approach.
Very structured, yes.
All right, the moment of truth then. With this ingenious framework, this multi-stage training, how well did Computer Bell actually do? What were the headline results on real-world benchmarks?
The results were genuinely impressive. On the standard OSWorld benchmark, the model they call Auto GLM-OS9B, which uses the GLM-4-9B model as its base, achieved a new state-of-the-art accuracy of 48.1%.
48.1%. How does that stack up?
It significantly surpasses other leading models. For comparison, OpenAI's COA03 model hit 42.9%, UiTar's 1.5 was at 42.5%, and Anthropic's Claude Sonnet 4 model managed 30.7%.
Wow, so clear jump ahead of some major players. A substantial leap, yes. And what's really telling is that a remarkable 64% performance gain came directly from the reinforcement learning stages, including the Entropulse effect.
64%, just from the RL.
Just from the RL part. That's a massive validation of their RL strategy, including Entropulse. It shows it wasn't just the initial BC training, the learning by doing part was incredibly effective.
That is a huge gain from RL alone. Really underscores the power there. But let's break down the impact of those individual innovations we talked about. How much difference did that API-GUI paradigm make, for example?
The API-GUI paradigm proved vastly superior to just using the GUI alone. On average, it achieved a success rate of 26.2%.
Okay.
Compare that to a GI-only approach, which only managed 11.2%. That's a 134% improvement.
Wow, more than double the success rate just by adding APIs.
Exactly. And the gains were even more dramatic in specific areas. In office tasks like spreadsheets and documents, there was a 350% improvement.
350%.
Yep. And in tasks classified as professional workflows, a 191% improvement. It really highlights the strength of using direct commands where structure allows for it.
Makes sense. And was it faster, too?
Oh, significantly faster. IU2 GLM-OS completed tasks using, on average, at most 1/3 of the steps required by the strongest purely GUI-based baseline models. So, not just more accurate, but much more efficient in execution.
Fewer steps, less time, fewer chances for error.
Got it.
And what about the training stages? Did the ablation study show clear benefits from each part?
It did, very clearly. The behavior cloning laid a solid foundation, getting them to 31.9% success on its own.
Okay.
The first phase of reinforcement learning brought substantial gains, pushing performance up to 42.0%.
Right, that RL impact again.
Then the Entropulse phase is interesting. Performance stayed roughly similar, around 41.5%, but it significantly increased the agent's action entropy, its exploratory behavior.
So it didn't necessarily increase the score immediately, but it primed the pump for more learning.
Exactly, it set the stage. And that enabled the final RL phase to then achieve the best overall performance, reaching that 45.8% mark in that specific ablation study configuration. It really shows how the stages work together synergistically.
These numbers really do paint a picture, don't they? How effectively these combined strategies, the hybrid interaction, the scalable training, the smart learning cycle, actually work together. It makes the AI not just capable, but efficient and crucially able to keep improving.
Precisely. It's the combination that's powerful.
Okay, this all sounds incredibly promising.
Yeah.
Groundbreaking even. But, no system's perfect. What are the hurdles that still remain? Where does the research need to go from here? What kinds of errors did they still see?
Yeah, they were transparent about the limitations. The researchers identified several key error types. The most common, actually, were multi-application coordination failures.
Okay, what does that mean?
That accounted for about 34.4% of errors. It's basically when a task requires seamlessly juggling information or actions between different software programs, like, say, copying data accurately from a web browser into a specific spreadsheet cell, and then maybe using that in a presentation slide. That coordination is still tricky.
I can imagine. Lots of potential fail points there.
Definitely. Then there were visual perception errors, about 25.8%. That's where the agent just misinterprets what it's seeing on the screen. Reading text wrong, misidentifying an icon, clicking the wrong button because it looks similar to another one.
Okay.
And operational illusions were about 14.2%. That's kind of subtle, where the agent thinks an action it took had a certain effect, but it actually didn't, or it had an unintended side effect.
Like clicking save, but maybe a dialog box popped up that it didn't notice, so the file didn't actually save.
Exactly that kind of thing. The remaining 25.6% were grouped as other miscellaneous errors.
I remember seeing some specific examples in the source material, like the agent misunderstanding a task about appending B, the HTML tag, to lines in a text file. It just kind of echoed the content back instead of actually changing and saving the file. Or another one, failing to change the theme in GIMP, the image editor, from dark to light because it clicks slightly in the wrong place. I once tried automating my own email sorting simpler than this, and it went haywire, archiving crucial client emails into junk because it misread one tiny visual cue. It's a good reminder of just how complex and, frankly, finicky this desktop environment can be, even for us humans trying to script it, let alone an AI navigating it live.
It truly is. Those examples really underscore the nuances and the ongoing challenges, and they directly feed into the future directions the researchers outline. First, they're aiming towards more robust performance. That means better handling of unfamiliar applications it wasn't explicitly trained on, dealing with new kinds of workflows, those tricky, rare edge cases. It also involves making the AI adapt dynamically when GUIs change unexpectedly, or when random pop-ups appear, and integrating more advanced multimodal perception, understanding images, text, maybe even audio cues together.
So making it more generally capable and less easily thrown off.
Exactly. Second, they're looking at breakthroughs in long horizon autonomy.
Long horizon.
Meaning moving beyond single discrete tasks like save this file or copy this text towards mastering sustained multi-step workflows. The big ambition here is developing hierarchical planning the AI, figuring out the high-level steps and the low-level actions needed to automate entire work streams, maybe even complex creative processes end to end. That would be a fundamental shift in productivity.
Automating whole work streams.
Wow. And finally, and this is critical, they are focusing heavily on the foundations for safe and aligned autonomy.
Safety and alignment. Crucial.
Absolutely paramount. As these agents get more powerful and more persistent, potentially running unsupervised for longer periods, ensuring safety, trustworthiness, and maintaining user control is non-negotiable. This means building things like granular permission systems, robust checks before an action is taken, maybe multi-stage approval processes for sensitive operations. The goal is to establish clear safety standards for these. Well, they call them intelligent digital collaborators, ensuring they always operate safely and truly in line with what the human user intends.
That's such a crucial point, because as these agents become more capable, more autonomous, how do we ensure they operate safely, predictably, and genuinely align with our intent and our values, not just blindly completing tasks according to some programmed rule? It's a huge, fascinating, and absolutely necessary challenge for the future, isn't it?
It really is. It's perhaps the central challenge as we move towards more powerful AI interacting with our world.
So today, we've taken a deep dive into Computer AI, a framework that's genuinely redefining what might be possible for AI right there on your desktop. From its really clever API-GUI interaction, that massive scalable training setup, to the innovative Entropulse strategy for continuous learning. We've seen how it's pushing the boundaries of autonomous desktop intelligence.
Yeah, this work truly lays important groundwork. It paves the way for more capable, more persistent, autonomous agents for computer use. It could fundamentally transform how we interact with computers day to day, really lifting AI capabilities to a whole new level. The potential implications for productivity, for how we leverage AI, they're immense.
So here's a thought to leave you with. Imagine an AI that doesn't just understand your desktop environment, but maybe even starts to anticipate your needs, adapting on the fly to how you work. What could that really mean for how you work or create, or maybe even learn? How much more productive could you be? What new possibilities might open up if the AI becomes less of a tool and more of a true cognitive collaborator?
That's the big question.
We hope this deep dive has given you a useful shortcut to getting well informed about this exciting frontier in AI, and maybe inspired you to think about the future of your own digital workspace. Keep exploring.